Consider the subspace W is equals to Aij such that Aij is equals to 0 if I is even of all 10 cross 10 real numbers, real matrices, then the dimension of W is A part 25, B part 50, C part 75, D part 100. Try this question.
It is 50.
Hmm. Tell me the reason.
See, it is 10 cross 10 matrix, so total number of element would be 100. But even number rows are zeros. So we left with 5 rows with number elements. So 5 into 10, 50.
Hmm. The dimension of the vector space V is equals to A equal to Aij n cross n such that Aij belongs to complex numbers. Aij is equals to minus Aji over the field R is option A n square, option B n square minus 1, option C n square minus n, and option D n square by 2.
It is n into n minus 1. That is n square minus n. C option.
Reason?
Again, for the first entry, we have the n elements, and for the second entry, we have n minus 1 element because one number will be repeated. A12. Then we have n minus 2. Then we have n minus 3. So we have
Hello.
Yes, yes, ma'am. So,
Or you can say like this, that dimension of skew symmetric matrix over reals.
that is n into n minus 1 by 2.
Hmm. And in this question, dimension of skew symmetric matrix is asked over complex numbers. So twice of n into n minus 1 by 2. So n square minus n. Let V be the real vector space of all polynomials in one variable with real coefficients and having, please mute yourself, having degree at most 20. Define the subspaces W1 is equals to P belongs to vector space, P1 equal to 0, P1 by 2 equal to 0, P5 equal to 0, P7 equal to 0, W2 is equals to
Is it 5
5. No,
dimension? Acha, okay. It is 20 plus 1. 21 is the fact. And 21 minus 5. 16 होगा.
नहीं.
इंटरसेक्शन है वैसे तो फिर 5 1 2 3. Not getting.
What will be W1 intersection W2? P1 equal to 0, P1 by 2 equal to 0, P3 equal to 0, P4 equal to 0, P5 equal to 0, P7 equal to 0. So,
It would be then 1 2 3 4 5 6 6 here.
hmm. This is polynomials in one variable with real coefficients and having degree at most 20. So, degree of this polynomials will be n plus 1 means 20 plus 1, 21, minus number of linearly independent conditions. there are 6 Li conditions, so 15. Let V denote the vector space over R, and W is equals to F belongs to vector space V such that d to the power 4f upon d to the power 4 plus 2 d square f upon dt square minus f is equals to 0. Then A part, dimension of vector space is infinity, dimension of subspace is also infinity.
It's option B.
Reason?
See, this complex space C5. So
Complex
dimension
space
C over C, है ना? This vector space C5 AB, है ना?
C5AB is like vector space of continuous functions which are 5 times differentiable.
Oh, yes.
Hmm.
So over R, so it is dimension can be taken as infinity now because there's been so many continuous functions over R, infinite number of
Dimension of C5AB will be infinity.
infinity. And second one is D4, so we will have the 4 solution over here. Degrees 4
4 Li solutions.
for Li solutions.
Auxiliary equation will be lambda to the power 4 plus 2 lambda square minus 1 equal to 0. So here I can put lambda square as z, then it will be z square plus 2z minus 1 equal to 0. So this will be z is equals to minus 2 plus minus under root b square minus 4 upon 2 minus 2 plus minus 2 root 2 upon 2 minus 1 plus minus root 2. So z is this, therefore lambda square is equals to minus 1 plus minus under root. This implies there will be 4 values of lambda under root minus 1 plus root 2 minus 1 minus of minus 1 plus root 2 and minus 1 minus root 2 minus of minus 1 minus root 2. So solutions can be easily written. E to the power under root minus 1 plus root 2 x. Y into x is e to the power minus under root minus 1 plus root 2x, and y3x will be e to the power under root minus 1 minus root 2x. These are Li solutions. So dimension of W will be 4 na. So B part will be correct. Where A and B are positive real numbers, then dimension is equal to
it is 1.
Hmm. How you have done this?
I solved this equation, then I found two solutions. But y0 equal to y1, one constraint is there. So 2 minus 1, 1 I have. Because disconnected by one relationship.
Or you can take some values of a and b.
Yes.
So roots will be -3 and -2. So solution will be c1 e to the power -3x plus c2 e to the power -2x. Now y0 is equals to y1, means c1 plus c2 is equals to c1 e to the power -3 plus c2 e to the power -2. So I can take like this 1 minus e to the power -3 and c2 e to the power -2 minus 1. So from here, if I take out the value of c1, then it will be c2 e to the power -2 minus 1 upon 1 minus e to the power -3. Means value of c1 depends on c2. So there is only one Li solution.
Yes, ma'am.
So dimension of this vector space will be 1. 3 to 4, or I think 4 5 questions are more left. You can try them from Dr. AP Singh's book. Okay, those solved previous year questions. Try them. If you have any doubt, you can ask. Now next is disjoint subspace. Two subspaces W1 and W2 of the vector space VF are said to be disjoint if their intersection is zero subspace. That is, W1 intersection W2 is 0. Then we will say that two subspaces are disjoint. Examples: subspaces W1 is equals to A belongs to vector space V such that A transpose is equals to A, and W2 is equals to A belongs to vector space V such that A transpose is equals to minus A. These are subspaces of vector space B is equals to M n cross n R over R. Now tell me whether they are disjoint subspaces or not.
They are not.
W1 intersection W2. A belongs to vector space B such that A transpose is equals to A transpose is equals to minus A. So by combining these two conditions, I can say like this: A is equals to minus A, 2A is equals to 0 means A is 0. So they are disjoint now. Their intersection is coming to be singleton 0. 0 subspace na?
Okay, right. Yes, got it.
Second, subspaces W1 is equals to XYZ belongs to R cube such that X is equals to 0 and W2 is equals to XYZ belongs to R cube such that y is equals to 0. Tell me whether they are disjoint or not.
They are not.
Reason?
The element z will be there. If we combine x equal to 0, y equal to 0, but z is there. No? So z is not 0.
W1 has elements of the type 0, y, z, and W2 has x, 0, z. So their intersection will be XYZ belongs to R cube such that x is equals to 0 and y is equals to 0. Means it will have element of the type 0, 0, z. Where z belongs to real numbers. So clearly it is not equal to the 0 subspace. So it is not disjoint. Third, check this.
This is disjoint.
W1 intersection W2 will be 0 subspace because it will have all the conditions x equal to 0, y equal to 0 and z equal to 0. Means disjoint. So a small remark. Let W1 and W2 be two subspaces of the vector space VF, then W1 and W2 are disjoint subspaces if and only if dimension of W1 intersection W2 is 0. Because W1 and W2 are disjoint subspaces means their intersection is 0 subspace and its dimension will be 0 na, because the 0 subspace is LD. I have told you na, it is linearly dependent, so its dimension will be 0. So if W1 intersection W2 is dimension is 0, then I can directly say that sorry, W1 and W2 are disjoint subspaces. Now next is vector space as a direct sum of subspaces. Definition: VF is a vector space and let W1, W2 so on till Wm be subspaces of V, then V is said to be direct sum of W1, W2 so on till Wm if every element V belongs to vector space V can be written in only one way, means it can be written uniquely as V equal to V1 plus V2 so on till Vn, where Vi belongs to Wi. If a vector space Vf is a direct sum of its two subspaces W1 and W2, then we should have not only V equal to W1 plus W2, but also that each vector of V can be uniquely expressed as a sum of an element of W1 and an element of W2. Means if VF is a direct sum of two subspaces W1 and W2, then we should not only have this condition, but also each vector of this vector space V is uniquely expressed as a sum of elements of these two subspaces. and notation is V is equals to W1 direct sum W2. Now an important condition. So this is necessary and sufficient condition for a vector space VF to be a direct sum of its two subspaces W1 and W2. That firstly, vector space V can be written as the sum of two subspaces. Secondly, the two subspaces should be disjoint. Now let us see some examples. R square R is equals to x comma y belongs to R square such that y is equals to 0. Direct sum x comma y belongs to R square such that x is equals to 0. So this is one subspace. This is second subspace. R square over R can be written as sum of these two subspaces now. Can be written like this: W1 plus W2. Second condition is these two subspaces should be disjoint. Tell me whether they are disjoint or not.
Yes, they are disjoint.
R cube over R. This is vector space. I am taking three subspaces W1, W2, W3 as not three, only two, sorry. X, Y, Z belongs to R cube such that Y is 0, Z is 0, tell me, can I write this R cube as direct sum of these two subspaces? Both the conditions of this theorem should be satisfied.
Yes, they are disjoint. But yes, they are disjoint.
Are you sure they are disjoint? This is like x 0, 0, 0.
Yes, that is 0, y 0.
So their intersection will be of the type. In the intersection, I need to take the common conditions now. So I will take the condition as z equal to 0 only. In the intersection, common condition will come now. So this will be.
But in previous case, we have not taken like this. When we have 0, 0, 0 y z and x0 z, then there was no intersection. When we were doing disjoint subspaces, example 2, in the definition of disjoint subspace.
Because there were two different conditions, na? So in the intersection, I need to take both the conditions. There was no common condition, na?
There was no common condition. Yes.
That's why I have taken both the conditions. When there is no common condition, then I need to take all the conditions of W1 and W2 in its intersection. But when there is a common condition, then I will take only the common condition. So this will be like this. So this is not disjoint, na? Not disjoint.
Okay.
So I cannot write RQ as a direct sum of these two subspaces. Vector spaces R cube only over R. Subspaces x is equals to 0.
They are also not disjoint.
What will be its intersection?
It will be y0, y0. Y is common, no? Y we have common intersection as y.
0 by 0. This type, na?
Yes. Yes.
So it is not just disjoint. So I cannot write R cube as direct sum of these two subspaces.
They are disjoint, so it can be written as direct sum.
Reason?
We have done it. It is A will become 0.
Disjoint. So we can be written as a direct sum of these two. Now next is complementary subspaces. Let VF be a vector space and W1, W2 two subspaces of vector space V. Then the subspace W2 is called complement of W1 in V if V is direct sum of W1 and W2. Means if V is a vector space, W1 and W2 are two subspaces, and if I am writing this direct sum, then one subspace is a complement of the other. So this is the definition of complementary subspaces. For example, these are two subspaces of R square. Now any vector x comma y belongs to R square over R can be written in one and only one way as x comma y is equals to x0 plus 0y. This is like this now, x into y0 plus y into 0, 1. In starting of direct sum, I have told you that every vector of this vector space can be written as the sum of elements of these two subspaces. So I can write this like this, where x0 belongs to w1 and 0 comma y belongs to w2. Also, if I see what will be their intersection, this is my x-axis now, this is y-axis. So their intersection will be 0. 0 subspace now means it is disjoint also. Therefore, R square over R can be written as a direct sum of these two subspaces. Means W1 and W2 are complementary subspaces. Is this clear? In
Yes,
doubt? Okay. Now I am giving you one question to try. Tell me whether this will be subspace or not, complementary subspaces or not.
It is not.
Firstly, this is yz plane.
YZ plane x is equal to 0. And x axis y and z 0. That is x 0 0.
Now, if I take any vector from this vector space V, I want to write this vector by using the elements of W1 and W2. So tell me whether I can write this or not.
W2 can be written as x 1 0 0.
I can simply add both the terms. Then I am getting this now.
Yes.
Simply this. Where 0 yz, this element belongs to W1 and x00 belongs to W2. And also, what will be their intersection? Here x is 0, here y is 0, z is 0. So their intersection will be 0 0 0 subspace na? This is disjoint also. So R cube over R can be written as a direct sum of the given two subspaces. So W1 and W2 are complementary subspaces. Example 3. This is xy plane and this is yz plane. Try this.
Here the intersection is not 0. So we can't written as a direct sum.
Here z is 0, x is 0. And one more thing, if I try to write V3 as V3 means R cube as W1 plus W2. Then, and I told you that the representation should be unique. So here I can write xyz as x comma 3y upon 4 comma 0 plus 0 comma y upon 4 comma z. Add both the terms, you will get this term only. where x 3y upon 4 comma 0 belongs to w1 and 0 comma y upon 4 comma z belongs to w2. Now it can be represented in one more form.
We can take 1 by 2, 1 by 2 both. 1 by 2 by 1 by 2 by.
Yes, we can take, there will be many representations. In short, representation will not be unique. So that's why it is not a direct sum. So when it is not a direct sum, I cannot say that W1 and W2 are complementary subspaces. W1 and W2 are not complementary subspaces. बिकॉज कॉम्प्लीमेंट्री सबस्पेस होने के लिए सबसे पहली कंडीशन ही यही है कि वो डायरेक्ट सम होना चाहिए. Now last concept of this chapter, existence theorem. Do you remember existence and extension theorems in linear algebra? You might have studied in graduation or post graduation.
No, ma'am. Not remember.
I am discussing its statement. Every finitely generated vector space has a basis. Means if I have a vector space finitely generated means firstly its dimension should be finite, then it has a basis, and second one is extension theorem. Every linearly independent subset of finitely dimensional vector space V can be extended to form a basis of V. So let us discuss some questions on this. Let Pf be a vector space having dimension equal to n and S be a subset of V such that cardinality of S is 10. If S is Li, options are n is greater than equal to 10, n is less than equal to 10, none of the above. If generator of S means vector space can be generated by this subset S, then sorry, n is greater than equal to n, less than equal to n, none of the above. So by seeing these two theorems, can you tell me which theorem is to be applied in the first part and the second part? Here it is. Firstly, vector space V is a finitely generated vector space. S is a subset of V such that its dimension or I can say cardinality is 10. S is Li. I can directly apply extension theorem here. Every Li subset, S is a Li subset of finitely dimensional vector space V, can be extended to form a basis for V. Now, if I am extended anything, then its and dimension of vector space was n. So if I'm extended something, then it will be greater than 10 na? Because cardinality of S was 10. So when I will extend it to form a basis for vector space V, then it will have n greater than equal to 10 because of this extension theorem. And if this S is finitely generated, then it has a basis. So if S is a generator of this vector space V, then it cannot have more than 10 elements na? Is this clear? Because S के पास already cardinality 10 है और ये finitely generated है vector space V से, तो अगर ये basis बनेगा, basis में हमारे 10 से ज़्यादा elements नहीं हो सकते ना? Yes ma'am. So इस वजह से इसका आंसर B पार्ट होगा. ठीक है. कहीं जाने के लिए बुलाया आपको? नहीं वो कहीं जा रहे थे तो मैं कहा गेट बंद कर लेना. अच्छा. Let Ms be a vector space having dimension of this as 10 and let S contained in V. If cardinality of S is 11, then A part S is Li, S is Ld, can't say. So now tell me which theorem is to be applied in this first part and then this second part. Dimension of vector space is 10 S is a subset of V.
So S with dimension is given. So second theorem can be applied in first part, extension theorem. But to form a basis of V. So there is one question. See, dimension of V is 10, right? If subspace S is a subset of V, so S cannot have more dimension than 10, then it will be linearly dependent.
यही था, सही समझा आपने कि यहाँ पे cardinality of S is greater than dimension of V. Means S is LD, linearly dependent. So B part is correct here. And here I can apply existence theorem. So if S is a generator of this vector space V, then its cardinality should be 10. It is compulsory. But here its cardinality is 9. Cardinality of S is less than dimension of vector space. That's why it cannot generate the complete vector space V. So B is correct. And here converse is not true. Means if S is LD, then I cannot say that dimension of S is greater than dimension of V. Counter example. V is equals to R square over R. Dimension of vector space is 2. I'm letting this as N. Take this set. Obviously, I need to take a LD set only. This is LD. What is the dimension of S? Tell me, what is the dimension of S? It's 0. No, sorry. It will be... dimension is, sorry, cardinality. Cardinality. Cardinality of S. So it is R square. R square over R. Cardinality will be 1 only, na? There is only one element in the set. Okay. So here I can clearly see the dimension of vector space was 2, but cardinality of S is 1. So converse is not true, na? Here it should be 0, 0, na? Because I am taking R square. And what about this? What will be the cardinality of this? And firstly tell me, is this set LD or LI? This is LD. Because it has a 0, 0 vector. Cardinality of S will be 2. So now also converse is not true. So this topic is completed here. Let us practice some question on this topic also.
It is B option.
No. Answer is D option.
If W1 is not equal to V, then solution of V minus V W1. W1 is subspace. Button.
So to discard the first three options, I need to take some examples. V is equals to R cube. Now clearly vector space V can be written by the help of these three subspaces. Spanning of W1 union W2. It will be W1 plus W2 means XY 0, where XY belongs to R, and letting this as A. Spanning of W2 union W3. Lastly, spanning of W3 union W1. Now I need to check that whether I am able to write A union B union C as V. I have simply applied the definition of union. It is OR now. Intersection is AND. Union is OR. So this cannot be written as vector space V now. Is this clear? Because if I take any vector,
So say W1 union W2 is only when subspace and one is contained in other, and if it's not given, it is contained. So we can't say.
W1 union W2.
It's a subspace only when one is contained in another. So then only it can stand.
You can say like this also. So 1, 2, 3, this element belongs to R cube, but this element does not belongs to A union B union C, because any one of the entries should be at least 0 now. So this A option is discarded. So for option B also I will take one example. E is equals to R square. Hmm. W1 intersection W2. What will be W1 intersection W2?
It is 0, 0.
Hmm. And this is also 0, 0. And I need to check that W1 intersection W2 plus W3 should be 0. W2 plus W3. W2 plus W3 will be complete this R square only. So what will be its intersection? It will be definitely not equal to 0, no? And it was mentioned that it is equal to 0. So option B is also discarded. Lastly, option C. It was saying that W1 plus W2 is equals to W1 plus W3 implies W2 is equals to W3. W1 plus W2. What will be this? R square plus 0, 0 vector. R square only. W1 plus W3. Again R square only. Here. But W2 is not equal to W3 now. It was mentioned that if W1 plus W2 is equals to W1 plus W3, it implies W2 is equals to W3. So option C is also discarded. Option D. W1 is not equal to vector space V. This implies spanning of V minus W1 is V. अब clear है ये वाला part? W1 is not equal to vector space V. V minus W1. W1 is a subspace of V. And means it will be a subset of V. So if I remove W1 subspace from V, then also the spanning set will contain vector space V only, na? Because W1
Yes.
was a subspace of V. That's why option D is correct. Sorry. Try this.
मुझे इसका आंसर तो पता है, पर मुझे इसका सॉल्यूशन क्लियर नहीं है। इसका आंसर बी एंड डी है, पर सॉल्यूशन मुझे क्लियर नहीं है इसका।
We are given that C is a n cross n matrix. W is the vector space spanned by this. So अभी तो वो वाला टॉपिक पढ़ाया नहीं, बट आई थिंक पहले करा होगा कभी तो रिलेट कर पाओगे. So I can write characteristic polynomial of C of a n cross n matrix basically. Lambda to the power n plus a1 lambda to the power n minus 1 a2 lambda to the power n minus 2 so on till an. This is like this only, no? Like if it is a 2 cross 2 matrix, then characteristic polynomial is lambda square minus trace of matrix A lambda plus determinant of A. Do you remember this characteristic polynomial concept?
Yes, ma'am.
So this is characteristic polynomial. We also know that every matrix satisfies its characteristic polynomial by Cayley-Hamilton theorem. Means matrix is C, so it will satisfy this polynomial C to the power n plus a1 C to the power n minus 1. From here, I can take this Cn on left side only and remaining entries on the right side. Minus a1 C to the power n minus 1. So, are you able to see that Cn is a linear combination of the elements of which set? I, C square, CQ, so on the C to the power n minus 2 and C n minus. Similarly, if you will see that C to the power n plus 1, C to the power n plus 2 and so on. I am going till C to the power 2n because in the question itself I was given that W is a vector space spanned by these vectors till C to the power 2n. So that's why I am taken till C to the power 2n. This can be written as a linear combination of the elements of the set, this same set. Therefore, it means that this set also spans the given set W. Now, I am getting spanning. If this set is Li, then what can I say? Spanning and Li will form the set as a basis for W. This implies it will be a basis for W. So if it will be a basis for W, then its dimension will be n. There are n elements in this, no? And otherwise its dimension will be less than n. The similar examples we have done for extension and existence theorem. Because if this set S is LD, then its dimension of C is 2n, and then dimension of this W will be less than n. If it is Li, then it will form a basis, and basis will contain these n elements. So dimension of W will be n. Otherwise, its dimension will be less than n. Means dimension of W is at most n. So by this B part is correct. Now you can also say the dimension of W is also at most 2n, because n is less than 2n. Because if dimension of W is at most n, then dimension of W will be less than equal to n also. So that's why answers are options B and